that's how it's going to look like. And it's a very loaded image. First, there'll be lots of computing. Computing will be very powerful. Very powerful right now. In 2042, we cannot even imagine how powerful it will be. First, it's all pipe dream. So 27 years from now, making predictions is very difficult. So it's essentially like a sandcastle or a cloud castle. So whatever we're talking about here, I view it as very vaporous. So the cloud symbolizes this. But at the same time, the cloud in computing right now is a very loaded word. It's something that people use and think that that's how things will, the trend that things will go in high performance computing. So a lot of data will reside somewhere on the cloud, not in your machine, but somewhere out there. And then also, when I saw this image first, when I looked at this person, it looked to me like he has wings. Well, so I think it may symbolize that to actually get access to the power, we'll need to grow some wings so that we can fly, and that's a challenge. Now, when Angela first mentioned the event and the task that is presented to us, which is making forecasts and making predictions. Well, forecasts and predictions are words that people use, but in science we use another word for this, which is what?
Guess.
We use guesses?
Tell stories.
Well, we use predictions, yeah, but predictions in this case is mostly extrapolations. In order to make predictions, we have to have a theory and or a good model for how things will evolve in the future. But when we don't, which in the case of computing, I think we don't have a very good model of how things will develop yet because technology trends are not obvious. It's essentially extrapolation, and I thought that we're not supposed to teach we're supposed to teach our students dangers of extrapolating. So the exercise we're engaging in today is a little bit counter to that. So John mentioned in the beginning that it's difficult to make predictions, especially about the future, but that's because in most cases you don't make predictions, you're extrapolating. That's what's difficult. You can explain why it's difficult. And it's illustrated very nicely in this cartoon. That you have two data points and you try to extrapolate it to the future, you very often get silly results. And at first, preparing for this, I thought, well, the way we'll go about it is we'll ask people to look 27 years back and then look at what we have today and then extrapolate based on 2 points. But then I remembered this cartoon and I said, no, you can't have 2 points. And there is, of course, anyone will tell you that 2 points extrapolating just based on 2 points is very dangerous, right? So we decided that we need to use more points. And so probably with the same result. But in thinking about this, I decided that we actually need to first talk about a few points of which we can extrapolate, which means reviewing a little bit about the history of computing in our department at the University of Chicago, somewhat more broadly, but focusing on our department. And so this is what we'll start with, and in what I'll present, most of it is not something I witnessed, and so I had to consult people who actually did witness its developments, most of them. And so special thanks go to Dick Miller and Peter Vandervoort, who filled in a lot of things for me, and actually in preparing for this, I learned most of what I'm going to tell you, so hopefully it's interesting, because it was interesting to me. So first of all, going back to 1930s, 1940s, of course people were computing all the time, people were doing calculations, but by 1930s, calculations were becoming complex, and individual theories were no longer able to handle. Of course, the famous examples are Los Alamos during the war, when there were parallel computations by armies of women with mechanical calculators doing computations. But actually, individual researchers like Chandra also used computers, and they were human computers. In this case, you can see one example in paper with the co-author Donna Albert and something I didn't know, but Peter Donna Albert was actually for 30+ years was essentially a human computer for Chandra. She would do complex calculations by hand. And you can see that she actually was, Chandra used her contribution as being essential to the work, so she was a full author on the paper. And again, so the famous example for the human computers was Los Alamos, and this is also, there's a Chicago connection here, because it is at Los Alamos that Fermi got exposed to computing, both by humans and by actual computers when they appeared in 1945. And he very quickly realized the power and potential of these computers, because Fermi himself was actually doing a lot of computations by hand. Reportedly, when he was suffering from insomnia in the hours of the morning, he would do Monte Carlo calculations in his head. And that would surprise his experimentalist colleagues by actually making predictions, supposedly guesses, for what the experiments will show, after doing a rough Monte Carlo calculation in some morning hours. So when he saw that computers can do arithmetic, he quickly realized that actually a lot of those computations can be transferred to the computer. And one of the first numerical simulations, or numerical experiments, if you wish, was the famous Fermi pasta-Ulam problem, which was a system of masses, or weights, connected by springs. And springs were linear, so there was Hooke's law, but with a small nonlinear term, which introduced interesting things into the problems, to weaken nonlinearity. And they found the surprising result that nonlinearity was preventing the system from reaching equilibrium, and equipartition, and so on. And it became very famous and led to a lot of follow-up work and actually development of concepts like solitons and so on. But what was known widely is that the actual computations in this case were done also by a woman, Mary Zinglu, and who wrote the program. And before she wrote the program, she wrote this algorithm. So this is how you actually write programs. If you're serious, you first have to do something like this. And in this case, she wasn't closer to the paper, even though the paper said that the paper is by Fermi, Pasta, and Ulam, but the work was done by Fermi, Pasta, Ulam, and Zinglu. So there was diverse opinions of what the work of a programmer or computer expert was worth in terms of attributing authorship. The connection to his history of our department is also Srinivas Metropolis, who was actually running the computer on which these calculations were done, so-called A&Aph at Los Alamos, which was successor of first manual computer that was built at IIS by John Van Neumann. And Metropolis was famous, of course, for many people know him through Metropolis algorithm. But not many people in this room, I didn't know this until I was preparing this. But Nick Metropolis was actually a professor. First, he was our graduate, that's one. And second, he was a professor at the University of Chicago for 8 years, from 1957 to 1965. And the reason he was at Chicago is because Fermi was very enthusiastic about computing when he was at Los Alamos, and so when he came back to the University of Chicago, he was lobbying very strongly to create a computer center here. He didn't live to actually see this idea come to fruition, but it did come to fruition about 10 years later. Things didn't take time. And it sounded to me like the story was like IME today. Essentially, somebody got this idea, and then they said, okay, this is great. We're going to bring a powerful, famous guy from somewhere else, and we'll build a building for this institute. And that building was this one, which many people in this room, I'm pretty sure that more than half of the people in this room don't know what this building is. How many people don't know what it is?
Who don't know this building?
It's a good fraction. This used to be Astronomy department when I came to the University of Chicago. This building was just behind this wall over there. It was behind the wall, behind the hallway of this building. And it was called Astronomy and Astrophysics Center, but actually the building was built. It was a state-of-the-art building built in the late 50s, built for this Institute for Computer Research, for which Nick Metropolis was the founding director. He was brought here to the University of Chicago just for that. And he did found the institute. He built, at this time people still built machines. So he actually came, they bought tubes, whatever, and they built the X3 computer here in the basement of this building.
With the roaches, right? With the cockroaches.
I assume that at that time there were no cockroaches. But I don't know. I wasn't there. So Cockroach is a joke of people who actually did occupy the space much later, decades later. So Dick Miller was part of this institute, and in the early 1960s, he actually started doing in-body simulations. I actually don't know how he made this transition, but his PhD thesis was on photometry of galaxies, doing essentially purely observational experimental work, but then he switched to doing theory. I think it just reflected that things were quite different. People were much more flexible in working on different types of problems. And this is an example. So this is an actual paper on stability of the gas. This is from later, but the first results that he was getting with the X3 were actually using about 100 bodies integration. He discovered the Miller instability by something that just reflects the state of numerical calculations, numerical approaches at that time. He saw that he was simulating physical system, so he decided to test his calculation by checking that it's time reversible. So if he just makes all accelerations, all the gravitational accelerations change sign, then things will just evolve backwards to initial conditions. And when he tried that, he found that they don't. You evolve self-gravitating system, and if you change accelerations back, they don't evolve to the same locations. That's how he discovered that self-gravitational systems are chaotic, something I heard a colloquium the last week by Scott Tremaine. This, of course, was somewhat known, but not widely known, and this became known as Miller instability. The small numerical errors in a chaotic system actually lead to divergence of trajectories and lack of time reversibility. For a system that is formally should be time reversible. This brings up the whole host of issues in numerical computing. For example, once you realize something like this, doesn't mean you can't trust anything about the calculation. The answer is no, but why the answer is no is actually quite complicated issue. Anyway, so this became known as the Miller instability, but even 10 years later, when Dick was publishing papers on the dynamics of galaxies, he did simulations which produced some of the first simulations which produced spiral arcs in yeah, you can still see it in 74 paper. It is a pleasure to acknowledge the use of X3 computer. So the upgrade cycle at that time was not as fast as today. So when they built X3, it actually was useful for 10-15 years for computing. In the late 1970s, this was definitely not the case anymore, and they moved to using A&Aph computers. So this is one of the papers that used A&Aph computer, which involved several people in our department. And many of you know this guy. I don't know if Dan is in the audience. He was here yesterday. Ben Welty and I, you probably know him as an observer. That's how I knew him. But he actually started out with a series. That's another example of people converting from one field to another, one type of work to another in the 80s. And this was a very productive collaboration between Peter, who was serious, who was providing analytical model for initial conditions, and people with numerical simulations and analysis. And at that time, they already used close to supercomputer at NASA Ames Research Center, A&Aph 4. Dick's most famous contribution were actually also using A&Aph 4 in the late 70s to do what I think was definitely one of the first structure formation simulations. So this is an excerpt from the paper in '83, which started from a Poisson initial conditions and then ran 100,000 particles. At that time, it was a pretty incredible number, it was 64 cube grid. Ran a gravitational collapse and expanding universe and found that it forms clusters with voids, subsequently look like filaments. If you look at the sort of n on the function of time, the simulation, the first in-body simulation Dick made sort of right there with R set and one corner in the early 60s. This simulation was in the simulation were done by people like Frank and Stasio, some of the first structure formation simulations, roughly the same number of particles, so it was somewhat larger. Now, what Dick showed me after I talked to him about this particular work is a letter from Peoples that actually, so this was published in 1983, but at that time, publishing takes a few years in the making. So this letter actually dates in 1980. It's from Jim Peoples. And at that time, comparison with observations was done in a very different formal manner. So the letter starts with, "Dear Dick, I quote Matt Rose on your movie. It really does look like the universe." So that was successful test of the model. But you can note that he talks about movies. So at that time, they not only produced 100,000 particle simulation, but actually made movies that are still too high resolution to display on this screen. They're 4,000 by 4,000 on analog 60mm film. Our library has it. And the letter ends with, I very much hope that you will keep up the work on expanding the body models and we can get together to discuss what might be done with them. Most of the letter is actually about numerical effects affecting results. So that's very typical for comments you receive for numerical solutions. And he says, have fun with media. Now, you know, seeing this letter actually makes me wonder about the progress because, you know, with email, I don't think you'll receive this type of letter. You will receive this type of email with this lens, with this colloquial, with equations embedded. And also, I don't think it's so easy to actually save email for 35 years. So Peter just had it, so he had it in his folder. I think all my emails will be gone in 35 years. Right. So late 70s also we're experiencing strong changes in computing hardware, and the first departmental server came about. And this was from the gift by A&Aph Foundation, which allowed the department to purchase what was brand new DEC VAX server, and that was the first odd job. So most of you know that our server, because your email starts with odd job, and I never understood why this was odd job until I was preparing.
John York did that.
Okay, so I was told that graduate students come up with this. Was one your?
That's what I'm told.
Okay. So I always thought that this refers to what we do. And that made sense to me. But then I am not very well versed in American pop culture, so it came out as a character from one of the James Bond's movies, which was called a server, a Korean server that did everything, all the dirty jobs. Also, Dave Arnett joined the faculty, and he was here for 13 years, from 1976 to 1989. And he spearheaded research in numerical modeling of supernova explosions. So here's one example paper, which he did in 77, so this was late 70s. And what struck me, you can see that it was in Chicago, and what struck me is that this paragraph, you know, you can just take and stick it in any of the current supernova tornado papers. It says, the diversity of attributes expressed as supernova underlines the importance of it, but also suggests the danger of their use as Deus ex machina to close our ignorance. So some of the issues that we realized back then already still more or less on the table. Ari joined the faculty also around the time, and he did work with on modeling of AGN and protostellar jets. And this paper with John Golding and Bruce Rixell was, as I understand, one of the first users of PPM in Astrophysics. So here's Bruce Rixell, that's Ari. And John Blonding was your student, right?
He's my class student.
First student.
Yeah. Yesterday we heard about these adventures with the football sampler is coming.
Okay. And also there is connection to previous session to be made because John Golding wrote this paper with Catherine Fries, which I wrote about last night at the reception. And that's another illustration for how people were more flexible in the past. So graduate students take notice. You can write papers that are not in your area of expertise with undergraduate students, that on something that's not area of expertise of each one of them, and you can publish them in Nature. So the last 25 years, a lot of people will be more familiar with, so I'll try to go much quicker. But essentially there's connectivity. So there's a line that connects to the 70s as the Dave Arnett left in Chicago. Don Lamb, Bob Rosner, Jim Truran were here, and they, in the late 90s, they continued to work on compact objects in supernovae by organizing the Flash Center, which won a competition, very strong competition for the ASCII initiative for development of Flash code. And the Dave Arnett's former postdoc, Bruce Rixell, that you saw was also working with Ari, actually was one who took an active role in the development of the Flash code. And the first version was in 2004. There were 4 major releases, but 2015. I think thousands of people all over the world are using it now. This is an example of early flash simulation. This is a picture that was hanging in the hallways when I came to Chicago, because it was very high resolution, very amazing, demonstrating power of that two-dimensional planet, and it shows simulation of a thermonuclear flash on the surface of the neutron star. One of the famous results from the last 10 years from the flash code was this idea that the deflagration to detonation transition in supernova type 1a would happen when off-center flame breaks out on the surface and then wraps around the supernova surface and collides and detonates the ashes. This is something that was very, I actually became aware of this before I heard it from Dawn by reading this article from Leo Kavanaugh, who just passed away, which was very influential on me because he actually pointed out that not all simulations have to produce quantitatively correct results. He said that in this case, flash code, who knows whether the model of flame is correct, whether the details are correct, but what you can learn is qualitative features. You can get qualitative insight for how things could happen. Right? In this case, that the flame could be going around the surface and then colliding and shocking, and this is generic thing. Just like inflation is a generic idea that essentially almost doesn't depend on details of how it occurs. Here, details of the cavitation may not matter, but the main mechanism by which deflagration to detonation transition happens may stay, and simulation shows that. This was very relieving to me because it relieved the pressure that, that simulations will always be numerically accurate. I think it is true. A lot of calculations can show us qualitative insights, even if they're not correct to detail. So the deflagration detonation transition is something that actually Alexei Khakhov came up with. The idea for this, he came up with in the early 90s. And in 2000s, he joined our department. He was also carrying out independent simulations, also supernova type 1a. This is one of the simulations. And he's now carrying out very large data scale simulations at Argonne of something that's quite striking. So he's simulating shocks in the hydrogen gas that are aid to essentially help model experiments that are conducted to help with problems with developing essentially hydrogen as an alternative fuel. And so that is something that's not astrophysics, but uses techniques that are well developed for simulating supernova for something that's considerably different. So this is one example where techniques, in this case not technology, but code technology that was developed by something astrophysical gets transferred to essentially industrial technology. And then last but not least is something that Nick and I have been doing here is we're continuing the work that Dick Bielek has been doing in the 60s and 70s and 80s, and working on simulations of clusters and galaxies and how galaxies organize the universe, and so on. So with this, I'm going to transition to the panel discussion. So the future forecasts, and some of the panelists didn't like the forecast, so they used the word provocations. So here we try to be provocative. So of course, again, making predictions about the future is difficult, dangerous, silly, and is illustrated by another image here. And I was reminded for how silly you can look in the future by making these predictions by last night at the movie or the documentary, the Jordan to Palomar, this quote was mentioned. And I urge everybody to just keep reading these quotes daily. Whenever you get in a pessimistic mood or whenever you try to prognosticate for the future, just remember that you have to be careful because things may look very differently in the future compared to what they look to you at that time. And of course, to us right now, it looks very funny, but I'm pretty sure that they were saying this and they have good reasons for saying these things. So this is something I heard last night in the documentary, but the similar thing was stated by Albert Nicholson in 1894, and also by Lord Kelvin in 1900. And look at this. I mean, and this maybe says something about, we heard some predictions today about dark energy or tensor to scalar ratio. You know, they'll be still measuring things that minus 4. Of course, it's all joking, but look at this. There's nothing new to be discovered in physics. All that remains is more and more precise learning. When you think about measuring W or Hubble constant, you know, to increase in accuracy, I mean, that sounds very simple. But then things were completely broken open by new developments, completely unexpected developments. And if I have to make predictions, I think the expectation should be that there will be new developments that will break things open. Also, having said that this is prognosticating is silly, I should say that this is not the first time people make predictions for 2042. Most of you probably don't know this, but in Russia it's pretty famous. There's a book written by William Eckhardt in 1986. It was very young at the time. It wasn't written in the USSR. He actually immigrated first. And then he wrote a book called Most of 2042. And in this book, he predicted that in 2042, Russia will be ruled by the Communist Party of State Security. When I read this book first in the early 90s, I was like, wow, how silly it is to make predictions and just because in the future, things look very, very different compared to what he predicted. But now, 20 years later, it's actually starting to look more so. So I think he knew something about the underlying trends and underlying dynamics. And if you do that, then the prediction can actually be quite robust long term, maybe not in detail or short term, but long term. So in order to make predictions, we use this analytical approach, which is actually illustrated in this image. I don't know, anyone know what this is?
It's a planimeter, isn't it?
I don't know what planimeter.
Planimeter is a thing you run, a thing around to measure the area of something you run a pencil around.
Oh, so it's not a
Spectrum analysis.
No. It's a computer. And it was a computer invented and designed by Fermi, but built by somebody else. I forgot the name, but it's called Fermiac. And it's a computer it's a mechanical computer, but it's a computer for doing Monte Carlo simulations of neutron scattering. So the neutrons, these are different materials. So it's really circular, it's not in a bomb. But the different layers are from different material. And essentially the machine was predicting, by some randomizing action, was predicting where scattering would happen. And then it would change the apparatus when the neutron would go from one material to another, so that the scattering per section would be different. Essentially, it's a computer for doing Monte Carlo simulations. It just illustrates that Fermi was doing Monte Carlo simulations. First in his head, and he got bored with it, that he kind of invented this machine. And then he saw that electronic computers were developed, clearly knew the potential of the computer for this type of calculation. But also that he used Monte Carlo sampling. And so we'll be making predictions by sampling. I thought it was interesting in difference of approach. When John was presenting predictions today, he, as a good observer, he did a survey, and a very complete survey. He took alumni and all the faculty and all the postdocs. So he just went and did the full survey of opinions. What we did is instead Monte Carlo sampling. So it will be not complete, but hopefully the answer will be approximately correct. So the panel, and also we decided to sample fully, so we're going to sample not just actually white, also in the panel. They're in the chair.
Oh, yeah, that would be fix. I'll definitely fix that. Yeah.
So
That was a great. Now we can take
in order for sampling to be meaningful, it actually has to sample the parameter space uniformly or fully, in a non-biased manner. So we try to make the panel to be representative of all layers of academic stages of career, so from graduate students, 15, to faculty, to postdocs, and researchers. So not everyone may know everyone here, so maybe I'll introduce. So Phil Mansfield is a second-year graduate student working on physics, structure formation. Daisuke Nagai. Daisuke Nagai is our former alumni, so he did a PhD here at Astronomy department in 2005 with John Malmström and myself. And professor at Yale University. Carlo Graziani is a research scientist here. Or I know actually know what the title is.
Research scientist.
And Nick Nevin is a scientist too at Fermilab and professor in our department. And Camilla Strus is one of the new additions to our department at Kavli Institute. You are Kavli fellow, but also president, university president fellow. Provost fellow. In computational, she is also doing computational physics. So we'll actually, I arranged the predictions roughly in alphabetical order. So Camille, you are first. But it's not exactly alphabetical, roughly. So Camille predicted that in 2042, the code development will follow the open source and crowdsourced models. We won't be developing codes in individual groups, but mostly it will be following the open source model. And a lot of computational research will be towards building infrastructure, maximizing available manpower. The high performance codes in 2042 will still be important.
Thank you, that was
The only question is, well, will it be photon 40 or will it be called something else? And teams will build large codes will be similar to teams that build large instruments and experiments in terms of division of labor, people doing specialized things with code development.
It's different actually. That was the Fortran one. The Fortran one's actually.
It was yours.
Well, it's actually Ralph Roskis was the director of People Supercomputer Center, who said that like 20 years ago. That I don't know what the computer code of 2040, 2050 would look like, but I know it will code for it.
So what happened to the actual field that's So you guys can pass on. Camille, do you want to say something else related to this?
Sure. I guess many of us are probably aware of things like Galaxy Zoo and Planet Hunters, right, where you basically have a huge massive amount of data and you don't know what to do with it, but if you build the infrastructure to use manpower from the general public, you could actually do some pretty cool things with that. And I think with the onset of a lot of open source learning tools like software carpentry, Coursera, more of the general public, they now have access to gaining this computational skill set. And when that's more integrated into the standard curriculum, or kids are doing this from a younger age, and that's just something they could do for fun just as easily as they browse the web, you just need the infrastructure to modularize the code you built, and people can plug into that. You can pick and choose the best of those to go into your scientific research, and I think that it'll also just engage the broader public. There are a lot of things that are happening right now that are already on that track, so that'll be pretty cool to see.
I think there's already some of this happening, but right now the open source still happens like in astronomical, using people in astronomical community. I think you are saying here something more radical, that people will open up to wider community, to harness large number of programmers, to build code, the way people harness manpower or citizen scientists to analyze data and like classify galaxies. And that idea actually I haven't heard before. So we actually will do this also somewhat differently. We'll, for each of these slides, and they'll be very different as you'll see, we also invite comments and questions from people. Yes, I
have a question. What about this short question? Quantum computing?
Anyone? That's why it's difficult to make predictions.
I think it's build it.
Anyone want to say?
Well, we're talking about technology, right? So there will be machines that you can program and run. What actually happens inside the code is maybe interesting to engineer. I actually don't care whether it's quantum computing, classical computing, or whatever.
Maybe you want
Super steam computing, but as long as it's a box that I can write the code and get the right answer, that's all I care about.
And you think Fortran will still apply?
Whatever is going to be applied, you will call Fortran. How it would look like, we don't know.
Anyone else?
I have a similar question to that. How does the structure of your coding need to change for quantum computing as compared to how computing right now?
Very much.
Yeah, I don't understand it. You could get microphone.
Maybe repeat the question.
So So the question was, how much does the structure of your program need to change if you're going to make use of quantum computers? And I'll preface this by saying I know next to nothing about quantum computers. But in general, the class of algorithms that get used for these types of machines are radically different from the ones that you see on classical computers. And I know there have actually been experiments where computer scientists have designed programming languages that are the type of thing that they would want to have operating on these machines, so that people can practice writing algorithms and doing these sorts of things. And I've played around with them before, and they're totally different from anything that you might be used to using in your own life. I don't really know how to program quantum computers, but it would not be as simple as just taking art and shoving it onto a quantum computer.
I mean, even without getting to quantum computing, if you look at the kind of violence you have to do to your code to get it to run on any one of the leadership machines that exist today, you're going to very people.
We'll discuss that.
You wind up with a lot of, I mean, it may be Fortran, but you wind up with a lot of directives in your code that have nothing to do with Fortran, just to make it route the code in the right ways. So, you know, we're doing that now. We haven't even done it on the computing.
A short comment at the Adler, they have Zooniverse, and they have people participate by computers to identify systems.
That's right. So I think the idea here is that this is something that could be potentially used for code development. So not for analyzing the data, but actually people, citizens, scientists contribute to code development on their volition, voluntarily in their free time.
So I don't see that in public GitHub.
Good question. So like I said, I didn't think about this idea.
Why is there no public GitHub of this code up that I could go to? Like, I don't write anything about looking at GitHub and searching what libraries are out there. And I know there are tons of people that really dedicate themselves to working on code projects such as this, that right now we're utilizing a lot of our strengths in science, but not so much in computer science and programming. There are many, many technologies that are created in the open source community just by that first person making it.
Yeah, I think you're just essentially stating that it's a good idea.
Yeah.
I agree.
And why don't you make one?
One of you two should.
Well, at first, as a brief microphone to Camille, I think the current trend that people are starting to do this. So it's beginning, but not in a big scale code.
I think a lot of the reason that there hasn't been a large-scale effort to do that sort of a thing is that the immediate payoff is not obvious to any given scientist in whatever stage of the career they're in. So the stage at which people would say set up a GitHub account and be super active, they're typically junior. And when you're junior, you're in science, you're not judged on building these tools, you're judged on scientific productivity. Even though in the long run, once you have this set up, potentially 5, 10 years down the road, papers could just pour out of this in principle, right? But I think it's that initial investment that is just really hard to get that off the ground. So I think if funding agencies could have funding directed specifically towards these things, which I think they've started to do that type of deal, that would have helped get started.
I mean, if you set up a GitHub account, I guarantee you'll have collaborators that don't want to do the science, that just want to work on the code immediately.
All my code's on
Okay. Well,
You should go visit him. So, especially for Camille, and being provocative at once this data is available to be analyzed by many people who are not in the academy, how is that going to change the face of publications and credit for their work, and how that's all going to be vetted?
I think it's already sort of come up with, for instance, the Zooniverse type science that they do. I just vaguely remember in the early days, because some of the founders of Galaxy who were over at my home institution for my graduate degree, they would talk about, like, oh, should we add them on in the acknowledgements as an actual co-author? And I think that's something that's going to be a continuing part of the conversation, because even across the branches of science and engineering, the question of how you allocate credit is up in the air. So as if hopefully science goes towards being more publicly accessible, we'll have to figure out how that will have to evolve and what that means for people who are in science and what that means for their career as well.
So how much, do you envision being manpower limited? Like, are we manpower limited right now? For instance, if we had infinite manpower right now,
Yes.
what would we be doing? What would we be doing that we're not doing right now? And will that get worse in the future?
Code development, but people who know what to do. Okay, so the question was, are we manpower limited? And from my perspective, definitely yes. You guys have mic. Yeah? Everybody?
Well, we said it several times here. If someone gives me half the cost of JWST, I will solve everything from the first principle. There won't be any need for any telescope ever again.
But that's because you want to hire more people, or we need more computational resources? We need more flops?
Both.
An undercurrent to these questions has to do with the way that computational sciences is taught from a basic level to graduate level. And I was just wondering, with your experience as a provost and also as a computational scientist, where do you see opportunities for change in the way that we do computational education so that the citizen scientists that are going to be contributing to innovation of the future will have deeper work or more meaningful work or in any way just better understanding of the universe? Like, what is the future of education that you see and how do we prepare for it?
I guess in terms of direction that I think education will have to go in, I think the material has to be as accessible to as wide a group of people as possible, and that goes for in terms of the various socioeconomic statuses that people have and how, like right now everyone has computers to start off with, but the access to smartphones, like people of middle, lower, and upper class almost all have smartphones at this point. So I think access to technology is starting to become cheaper. Next to that, with the internet, with open source courses, those need to also be made available and advertised more widely to, again, a wider range of people, at least in our country. And that is probably something that will help engage more of the general public, because if science is not seen as something cool, or science is not actually brought to the communities, it's not going to be kickstarted from that end. So I think there's that great presentation on coverage earlier this morning, right? And I think a lot of this is going to have to tie into that as well. If you want to tap into the full talent spectrum, you're going to have to really be proactive about doing that. So I think proactivity on parts of people from, say, UChicago is going to be a key seed to that success.
So we have quite a few predictions of that. So you want to say something?
Just want to say just a few words about this issue. I think computation and statistics are going to be the language for the upcoming sort of the next century society. I think I think the university is going to start to require, I think, the computation. This is something that we learn along the way as we do research. It's something that we all pick up. I think all of these are going to be offered as a boot camps and courses, and I think eventually it might even become some of the basic requirements as a citizens of the society.
It's like mathematics.
It's basic literacy.
Okay, so Carl, you get the microphone, right? Okay, you're next, and you have two provocations.
Astrophysicists reading code will be banned from running on supercomputers because they get too amateurs and wasteful and scarce computers like this. Consequently, professional supercomputing programming support will be essential personnel infrastructure for the future department, analogous to professional systems. Should I start getting beaten up by that?
Yeah, that's right. Just say condition will cease to be reproducible. They really did that, like people told me.
So the second one, and this one is more speculative, because of their fault tolerance issues in the generations of computers that are being planned, that imply that there's a possibility that with certain architectures, computations will just not be reproducible, in that you run the same computation twice on 10 to the 8 nodes, and starting from the same initial condition, you get two different results. So the output of computation is going to mimic experimental measurements, and you're going to have to ascribe error bars to your results. Well, that's kind of interesting, because if your model is becoming more and more like your data, what does it mean to compare the model to data? How do you do that? I think it will create some interesting, novel, and possibly scandalous.
What is a scandalous way?
Well, because I think conflating model with data is a controversial thing to do. It's a controversial idea, but I think there's an extent to which it will be necessary.
Well, let's open for the other panel members and anyone in the audience. Comments, questions?
I've been growing this weekend exponentially more ignorant. But I have a question in my mind always going around and around, and that is, yeah, we are learning a lot about the universe, about life, everything surrounds us, but at the same time, seems to me that every progress we make, more telephone, computers, the empathy we should have for life around us, for each other, for the future, is being missing. And I know this is an optimistic reunion here, but I couldn't avoid this sense of loss. I don't think I'm getting old. I saw the world a few years ago. I used to dive in Australia and in the China Sea. You go now, you see the deterioration, the brutality of what we're doing in this world. And I say, what all this means? Why this quest for more knowledge when at the same time we are destroying life and future in this time? So I don't know if you have any comment on that, but this was my feeling of loss.
This reminded me of one time, it doesn't happen frequently, unfortunately, but there was one time when I was a postdoc, there was internet failure, and everybody stopped working and filed out in the hallways. But the hallways were full of people, and people were just moving around, not knowing what to do, and they just started talking. And it was so great.
So I just wanted to comment on the first provocation that you mentioned. I find actually that things are going completely the other way, actually, for at least for now. In fact, I think when supercomputers first came up, they were scarce and people had to have nicely parallelized codes and run, things which could really be run on supercomputers. Nowadays, I find that I have gone to a lot of meetings, work with a lot of people, and they always mention universities have supercomputers and stuff, and now they run on a supercomputer, but you run on one core and run 100 different things with just parameters changed to run instead of. So I think in the sense that there are actually less sort of code meant for supercomputers and more people are actually just running maybe what you would call amateurish, but I think it's going to go completely the other way. Sorry.
Okay, so I phrased this to invite getting that one. And it does connect, I think, to a point that Camille had on our previous slide, which is the larger sort of collaborations of people that are going to be required in order to produce production-grade code that can run on leadership scale machines. These machines they're not designed to run the kind of embarrassingly parallel problem. I mean, you can run them, but there's no reason to build these machines You can run, you can run those kinds of calculations on a network of quick machines if you want, but that's not what these machines are for. That's not what you build.
I agree completely.
You build them for things like PDE solves, for large elliptic solves, and for many, for protein folding. And the problem is that they are such complex architectures in which it's so difficult to correctly route, to organize your data so to take advantage of the capabilities, that it requires very specialized technical knowledge to write code that is not wasteful, that it is not irresponsible to write, to run on these machines. And that's true of NERA at Argonne today. It's going to be much more true in the future. I mean, I think a good analogy is, I think everybody in this room can drive a streetcar. I'm pretty sure that there are 0 people in this room who could drive a Formula One car without killing themselves in the first 15 seconds.
No, but that's the point. The Formula One car became as cheap as street car, everybody would drive it. And that's exactly
No,
what's happening.
so these are not going to be cheap machines.
But universities can afford supercomputers.
Okay, but there's going to be a class of machines that we need to do the kind of transformational computations that we want to do. And in order to operate on those machines, we're going to need professional help. I think there's going to be a transformation of the culture, which is analogous to the transformation that went down about 20 years ago. When I was a graduate student, we all did our own sysadmin work. We mounted disks, we tweaked kernel parameters, crap like that that we shouldn't have had to do. Fortunately, graduate students nowadays can focus more on doing actual astrophysics rather than administering machines. The networks grew complex enough and enough machine, you have 200 Linux boxes in the astronomy department. It became a crazy way to run a system. And eventually the realization came that we need people like Valerie. We need professional sysadmins to help us so that we can concentrate on doing our own work. I think a similar thing is going to happen with programmers. We're going to need professional staff of people who know these architectures, who know the people at these facilities, and who can help us. We can give them computational kernels, and they'll have the specialized knowledge of the software stack, of the architectures and so on, and collaborating with them, we'll be able to put together codes that don't turn these machines into space heaters, that actually do something useful.
So, and I know that nobody comments on the second provocation, so I think about I 1 second?
Just
Many people think that computations are only producible now.
I just wanted to ask for clarification in view of what Andre told us earlier, that maybe computations don't need to be numerically precise, but they should be qualitatively interesting. So when you say cease to be reproducible, maybe they don't need to be reproducible quantitatively, but if they uncover something qualitatively interesting, that potentially should be reproducible, and so maybe it would be less standard.
For some applications, I'm sure that's true. For other applications, we're actually trying to do validation on experimental data. It's not true. You actually need some kind of error bound on your solution as well as an error bound on your data, so that you can compare the two and mean
I was just going to say, but model uncertainty is nothing new. I mean, we compare data points to models with cosmic variance. There's already sample variance for many n-body simulation just because there's a finite number of halos and stuff to derive stuff from. So that's not new.
You're right.
It's not a new thing, just a new type of error.
It's a new type of error that's going to have to be calculated and propagated in new ways. You can't afford to run this calculation 1,000 times and just take the variance of results.
I might point out that in climate science, this actually has a name. It's called the Hawk-Cloth effect. They've been studying it for some years. The divergence of irreproducibility.
Oh, but that isn't that due to the initial condition? I mean,
no, not initial conditions, models, divergence models.
But if you run the same model twice with the
Well,
exact same initial data, you get the exact same result. This is different. This is due to faults.
I understand, but there are similarities in the divergence solution. Irreproducible.
We're going to give Nick a chance to show his dynamic slide.
You just have to press the button, so you.
Oh, okay. So when do I need to press the button? Right now?
fact a model, right? It's not as a model, right? It's a model, it's a power law.
Different
And
ones
it's
here. Is the most powerful computer?
yeah, this is the first most powerful. This is the 500s. This is some of the first 500. Those are laptops. So by the way, the cheapest way to own the fastest supercomputer in the world is to take a laptop and go back 15 years. But so this is actually a model. We can extrapolate it. It's power law, right? So, and it's been power law since 1960s. So it's been already power law for 50 years. So if you extrapolate it, yeah, press. You get 1 iota flop. So our buzzword today is exascale, so we get real scale. So what I was trying to do is to estimate what you can do with 1 iota flop. And that's my next slide. So in galaxy formation simulations, we actually going to model a bunch of galaxies in technological volumes down to resolution that we actually have now. So in fact, it doesn't look very impressive when at first I thought we would get them great numbers, but when I got to this, it doesn't look very impressive. On top formation scale, we start modeling the whole galaxy with the resolution that we can now model small boxes, but we still need to wait for another 15 years before star formation and galaxy formation become one.
After 20.
Yeah, after 2042. So by 2060, there won't be galactic and extragalactic astronomy. There will be, I don't know, all galactic astronomy. Right? So it will be one science. Whatever, baryonic astronomy, whatever. But, and so 2042 is actually a wrong time to celebrate that. Celebrate 2060.
About 50 years ago, Martin Schwarzschild was running programs of stars evolving up the giant branch. And he found that his programs were running slower than the stars were actually evolving. And his conclusion was, once again, we were forced to think.
That was a good one.
That was also, I think it was also a qualified provocation.
That was a provocation.
Well, I don't know what you're planning. I'm not sure what the application and what's mine.
Kind of doctor.
So I want to go.
We try to think occasionally when we have free time on coding, but yet it's not very often.
I'll let you fight it out during the coffee break. What kind of thing to do? I want to get to that here, so I'll skip myself, except to say that I disagree with Nick, as always. And, well, yes, I agree, but solve is a loaded word. But I do think that Moore's law will break, at least in the way we compute things. So, so I want to get to Phil. This prediction. Do you want to translate it?
Sure. So we can all see my earlier comment about Fortran still being the programming language of the future. I think that despite the fact that we will be writing things in some version of Fortran, the parallelism is not going to be handled explicitly in the way that we do now. I think that if you look at current proposed solutions for how you would handle parallelizing, say, a galaxy formation simulation on an exascale computer, a lot of the tools that are used for this are very generic. They involve things like analyzing dependency graphs, thinking about things in terms of tasks, and a lot of techniques which could very easily be done by a generic runtime system, which is merely looking at the dependencies of different parts of your computation. And this is something that we could get the computer scientists to do for us. And in fact, there are many who have tried this and have been developing systems like this already. And I think it's entirely reasonable that for all but the very most numerically intensive calculations, that a lot of the labor that's being put into developing these codes can be alleviated by sort of relying on these.
Runtime systems. You want to explain?
Sure. So they, they analyze the data access patterns and these sorts of things as the system is running to figure out how to load balance across multiple cores. Because as you move up to larger and larger systems, this becomes an increasingly difficult problem. think questions about how you are going to distribute your problem load is something that gets talked about a lot when you're thinking about these types of systems. I do think the other 2 points that I brought up have already been discussed.
Any comments?
When you say runtime systems, you mean the actual computer would be analyzing this?
Yeah, essentially at the system level or some sort of system layer.
Not necessarily at the, it would have to be integrated with the system layer, but it's not necessarily that each individual machine has its own system that's running. Although I think a lot of the promising ideas for this are fundamentally tied to the machine and have to be thought of at the machine level. But there are things that exist now which are built a layer above that, which seem fairly promising.
So this comes from the idea that these machines will be too complex and too large to actually try to pre-plan what's going to happen on all these big levels. So you have to let the system sort of evolve, be flexible enough so you can adjust and balance the flow. Okay. Daisuke is, I think, some of the most optimistic predictions.
Okay, I didn't know that I have the most optimistic vision, but yeah, so I think the way we do cosmology is going to change. You're gonna learn how to actually use a complex system like galaxy clusters to actually do precision cosmology. I think we're gonna do, and with this, I think there are a lot of optimism for the sake, a lot of computation. Null power is going to be keep on going. I think we're going to, there are a lot of observation that's going to be planned. 30-meter class telescopes to large-scale survey. There's going to be a huge load of data. Challenge is to actually how to get the information out. I think the challenge for the galaxy clusters, when I was putting together the PhD thesis project, the challenge there was that the ability to measure cluster mass was uncertain by 100%. In 15 years, we came from 100% uncertainty to about 10% today. I think in next 20 years, I think we can actually go, keep on going, and keep going with that trend. And about 1% calibration of mass calibration of galaxy cluster, I think should be within reach.
The only comment to defend my claim that the Moore's law will continue. That's because from a psychological point of view, there is a huge pressure for supercomputer industry to actually stick up with this rate. Because the first company that will not match to it, it's something that can be put against it. So there's actually commercial and psychological pressure to maintain this at whatever costs. Right? So what it means that the machines that they will build, you have this mark on it saying, 1 good o'clock or whatever, right? It may not be possible to get 100% of its efficiency. You may not be able to get 10%, or maybe even 1%, but at least formally to actually lie on this line. It will be very hard to program on them. So those things we have to solve.
So I meant that in actual computing, we will not be able to do all. So the formal flows will continue to increase, but I doubt even that, but even if they do, I think the actual computing flows will level.
Well, for that I can contradict you with a quote from, not exact quote, but a phrase quote from a famous computational scientist who actually works at this department, who told me about 10 years ago when I just came, and we had one of those first conversations. He said that there's Moore's law, but on top of that, the rate of the performance of modular codes were actually squared of the Moore's law. Why is the exponent? Because the algorithmic improvements gave you another power of the same order. And so that was actually you. So then I can just use your word to contradict your statement.
But my statement was true back then, and I think it's not really true in the next 20 years. So we have a few more predictions, but we're also out of time. And actually, the remaining predictions, which were by Petros and by Don Lamb, I think this is also emphasizes what I started to say in the beginning. they're increasingly pessimistic. So John Lammers was very pessimistic when we talked about it. For the same reason, so hardware going sort of crazy and crazy complicated in terms of programming, something we already kind of discussed. But John was very, I wish he was here to convey his pessimism, because usually he's very cheerful. If you want to hear his opinion, just catch him when you see him in the hallway. And this is probably one single time when I saw John being very upset and pessimistic about the trend for high performance computing. And also Dick Miller gave a prediction, or one thing he said is that, which is true, we haven't discussed yet, is that even at exascale, the computers will use up tens of megawatts of power, which is about 5 to 10% of the nuclear plant. So that's not going to be cheap. And somebody will have to pay for it. So that's, one, going back to the people not being let near the machines, that connects to that, because the cycles will be quite expensive. And what Dick also said is that I'm pretty sure people will find a way to burn the cycles, depending on, but whether they'll get good science out of it, he wasn't so sure. And when I saw these pessimistic predictions and getting more and more pessimistic, I wanted to leave you with this quote. Because if enough people predict something, it will happen. This quote is from British novelist who specialized in apocalyptic novels. Thank you.